So I'm going to introduce, well, first myself. I'm Jennifer Hunt. I'm at Treasury, but I'm here more in my capacity as an economics professor at Rutgers. And to my immediate right is Larry Bucciarelli, who's emeritus professor of engineering and technology studies at MIT. And on his right is David Knight, assistant professor of engineering education at Virginia Tech. And on his right is Hal Salzman, professor and senior faculty member at the Bloustein School of Public Policy at Rutgers. And so each panelist is going to talk for at most 10 minutes. And then I guess like the other panels, you can ask a question right after their talk if you want, or we can hold it for, there'll be at least 25 minutes of general discussion at the end. And Larry's going to go last. Do either of you two have a preference about who goes first? Okay, so David.
Well, good morning. My name is David Knight. I'm an assistant professor at Virginia Tech in engineering education. I'm very happy to be here. And what I'll be talking about are findings from an NSF-funded study that was conducted by our research team, which included an array of faculty members in engineering and in higher education. The project directors were Lisa Latuca, who's in higher education at the University of Michigan. She was my advisor. And Pat Terenzini, who's now retired from Penn State University in the higher ed program there. We just sent out a report summarizing the overall study called 2020 Vision, Progress in Preparing the Engineer of the Future. And if you'd like a copy of that, I'd be happy to share a PDF with you afterwards. Our approach in this study was to figure out what seems to work to develop the engineers of 2020. So we've talked about the engineer of 2020 as having strong technical skills, but also a variety of other skills and competencies, professional skills, interdisciplinary competence, and contextual awareness. And our approach to do this was to run a survey-based study where we try to get a comprehensive understanding of the system. So we have data from 29 associate deans from 31 institutions. That was our sample in the study. Institutions of all shapes and sizes, bachelor's, master's, doctoral granting institutions, small, medium, large, public, and private. So it's a really good cross-section of the institutional sample within engineering. We also have data from 86 department heads, over 1,000 faculty members, over 5,000 engineering undergraduates, 1,400 engineering alumni 3 years out after graduation, and 1,200 community college students who are in pre-engineering programs who were planning to transfer into a 4-year program. So it's a really comprehensive understanding of the system. And what I want to do today is talk through some of the findings that will extend some of the conversations that we've been having earlier today and yesterday. So the first thing I want to talk about are what are alumni saying. So this is very similar to what Samantha found yesterday in her study with Sherry Shepard. And we asked alumni, what was emphasized in your undergraduate programs, and what are the skills that are important today? So we looked at those differences, and the largest differences with the largest effect sizes were lifelong learning, ethics, communication skills, project management, leadership, and professional skills. So knowing codes and standards, knowing deadlines, showing up on time. Those are the biggest differences between what was emphasized in undergrad engineering ed and what's important in the workforce. Some of the medium effect sizes were for teamwork skills and working in multinational groups. And the lower effect sizes were creativity and innovation, defining problems, and how to solve a problem. So it seems like what is actually emphasized in the curriculum is flipped from what everybody's been talking about so far as being really important for the workforce. So from a positive perspective, we can say that what we're doing in higher ed is actually working. So we're emphasizing certain skills, and it seems like graduates are actually developing in those skill areas. But we might want to think about what we're actually emphasizing, and that's what I'll talk about for the rest of my time, talking about what seems to work to develop an array of outcomes. So I'll start with our student approach, so looking at our data from undergraduates. And we followed an input environment outcome model. So what do students arrive with, what experiences do they have, and what outcomes do they leave with? We've thought about each of these outcomes independently and all of the outcomes together. So thinking about holistic pictures of students, so those who developed strong technical skills, but also strong professional skills and interdisciplinary competence. And what we found, no matter how we look at it, that the curriculum matters more than anything else. What is emphasized in the curriculum matters more than how we teach. It matters more than faculty interactions, and it matters more than co-curricular experiences. About 3 times the magnitude of the closest variable. In particular, emphasizing broad and systems perspectives in the curriculum is related to students' design skills, interdisciplinary competence, contextual awareness, and development of professional skills. So showing how what you're talking about connects to other disciplines, being very explicit about how different contexts influence that solution or whatever you're talking about, seems to be really important for the development of the engineers of 2020. I want to just add one additional comment. We have looked at some gender differences by programs in terms of structural diversity. So what percentage of women are there? And the programs that tend to emphasize broad and systems perspectives more tend to have more female engineers in those programs. So that ties back to something that Stephen Brown was talking about earlier. We also found that it's inappropriate to think about engineering as a field. There are different relationships between what matters in terms of student experiences and outcomes based on what discipline you're in. So the important relationships for civil engineering were very different from the important relationships for mechanical engineering and so on. So thinking about engineering as a whole field loses some of those different nuances. There are some opportunities to leverage the co-curriculum according to our data. So in particular, humanitarian and community service types of co-curricular activities were related to the development of interdisciplinary competence for students, as well as design skills. And also, participation in non-engineering organizations was really important for the development of interdisciplinary competence. And that makes sense. Those are the organizations where students are engaging with other students from business majors or from policy majors. So getting students to think outside the box of engineering is really important, and one way to do that is through leveraging the co-curriculum. Shifting gears now to some of the other things that we can control. Okay, what is it about the higher ed experience that we have full control over? We can control the curriculum, for example. And so one area that we looked at was the policies and structure for design courses. Everybody, faculty, administrators, no matter if you're looking at associate deans or program chairs, said design's really important. And this is where faculty say they tend to emphasize skills, non-technical skills like interdisciplinary competence and professional skills. It's also where assessment looks really different. So the assessment of those courses tends to mimic how projects are assessed in industry. We tend to assess things using project reports or group reports, presentations, as opposed to closed-ended problem solving where we're looking for one right answer. Unfortunately, we don't do design in the curriculum very often. So I just want to share a few statistics with you from our program chairs. Design, just in terms of being offered versus not offered, it's required in year 1 in 50% of the programs, and we had about 125 programs in our sample. Year 2, only a quarter of programs. Year 3, in 44%, and then everybody requires capstone design. If we look at programs that do not offer design in the first year, that's 28% of programs. Half of programs do not offer a design option in the second year, and a third of programs don't offer it in the third year. So we get this bookend of when students are actually experiencing design, and if that's the only places where they're developing these skills, it doesn't seem like a very optimal solution. We also asked about the different nature of design. So are students mixing with students who are not within their discipline? 28% of the first year programs mix across the engineering disciplines. So that's mechanical engineers with electrical engineers, or this could be a general engineering program. Maybe students aren't required to declare a major in year 1. Only 12% mix students in year 2 that way. 10% of programs mix them in year 3, and 22% mix them in year 4. 71% of the capstone programs are discipline specific. So there are only mechanical engineers working within mechanical engineering on their capstone design projects. And so we talked yesterday that that's not mimicking reality. So that's an opportunity for changing the system to try to get students to develop these skills such as interdisciplinary competence. When we look at interdisciplinary design programs, so this is mixing engineering students with non-engineers, only 6% of first-year design courses follow that model. None of them follow it in years 2 and 3, and only 4% of capstone courses mix engineering students with non-engineers, at least from our sample. Our data also show that students who are in those types of interdisciplinary programs have higher design skills when they graduate and interdisciplinary competence when they graduate. So it seems like that could be an approach for enhancing the Engineer of 2020 idea among students. The last thing I want to talk about are how can we change the system from a faculty perspective. Administrators and faculty, by and large, buy into a lot of the E2020 ideas. There's some room for growth in certain areas, such as diversity. We need to change the narrative away from the fact that diversity suggests quality of students. That narrative should change. And faculty aren't quite on board the notion of entrepreneurship. That's probably changing over time. But by and large, there seems to be some buy-in, but what's emphasized in their courses and what they're actually doing doesn't necessarily align. So one idea for why this is the case is that, and I mentioned this yesterday in my question, 70% of engineering faculty have no formal training whatsoever in teaching. And we're very open in our definition of formal training. This includes a one-day workshop in teaching. So if you don't have formal training in teaching these skills, the natural fallback is to teach the way that you were taught, or to stay within your bread and butter and teach what's related to your research. So I think we need to start thinking about professional development for faculty members to help them understand how they can incorporate some of these topics or emphasize interdisciplinarity using different kinds of examples into their courses. We do see some positive influences for faculty who are non-tenure track who came from industry. So they're bringing what they did in industry into the classroom, and there's differences in assessment, there's differences in what is emphasized in their courses, and this goes for design courses, for engineering electives, and for technical required courses for students. So it doesn't matter what kind of class you're looking at. So I think there's an opportunity to also leverage their expertise and help them guide some professional development within the university setting for their tenure track colleagues. And with that, I will conclude. Thank you.
Great, thanks so much, David. Questions for David? Yeah.
This is Amy, and I was...
Just hold on till we get the microphone.
I was curious on your... this is Amy Jevernick-Well from the University of Colorado. I was curious about your faculty training. Was that faculty training in teaching in general, or faculty training in teaching professional skills?
No, it was teaching in general.
Isabel Cardenas-Navia with Altavision Consulting. I have a question about your former industry folks who come in to be adjunct professors. So it's very interesting to me, how does that industry perspective, how does that play out in terms of, the metrics that you've looked at?
How does it play out in terms of what they're doing in classes? Or?
Yeah, yes, I mean, how
Sure.
do they bring that into the classroom, and what outcomes do you look at to see that it's actually making an impact that's different than a sort of traditional academic?
Sure. What they tend to do is bring in different forms of assessment, first of all. So we don't see the closed-ended single solution problems given to students by those faculty relative to their tenure track peers. They tend to be more group report driven, more presentations for assessment, so first of all. Secondly, they tend to bring in case studies more into instruction, so bringing in more of the inductive forms of learning, small group work, giving them real-world problems to think about as opposed to more of the textbook problems. And then what they're emphasizing in courses is different also. So showing the societal relevance of whatever topic they're covering, or connecting it to these larger issues, thinking about things from more of a systems perspective. We haven't connected yet those instructional practices by those faculty members to outcomes from students in their courses. I don't know that we can do that with our data in terms of cell sizes mapping to each other. But if we just look at the student data, those types of experiences do map onto the development of E2020 outcomes. So we could make the leap in logic there that they would have an impact. Thanks.
One more question, if there's one.
Proctor Reed with the National Academies. You were moving quite quickly. a lot of information to cover, but you talked about faculty and the issue of diversity, and I wanted to, if you could say a few more words about that in terms of buy-in. I was just curious.
Sure. That was the one finding where there isn't not necessarily a lot of buy-in. There's a lot of uncertainty in terms of where diversity belongs in the engineering curriculum, whether it's their faculty members' responsibility to include topics related to diversity. And one item in particular that we asked, does enhancing the diversity of engineering reduce the quality of students? That's the one where faculty members tended to be non-committal on either way. Surprisingly, department heads said that with respect to underrepresented minority students, there is a relationship between quality and diversity. So I think changing that conversation and maybe thinking about different ways of measuring quality or different ways of framing quality is a way forward to change that.
Great, thank you very much. And so let's move on to Hal.
Do up the music. And there we are. Okay. So I want to take kind of a broader perspective about the STEM issues, STEM pipeline, and engineering in particular. But I'm going to start with a question. I want to ask you all, think about when you were 17, what your occupational fantasies were, what you thought you'd be doing. How many of you today are doing what you thought you'd be doing when you were 17? Few of you? How many of you would want to be held captive to your 17-year-old self for all your future decisions? So the question here is, how much is the 17-year-old mind driving STEM policy? And at the core of it, we have a lot of questions that are framed around what a 17-year-old thinks, says he or she is going to do. And this is how we end up framing a lot of our concerns and policy. So the questions I want to talk about are sort of STEM, and then reconsider some of this flows issue about pipelines, and are we addressed at the right problem? So if we want to look at kind of STEM, you know, it's this thing that's got a lot of cachet because it's cute and has a lot of cleverness to it, but what I'll argue is nobody really knows what it means or what's in it. And there are a lot of ways to cut it. Just to quick cut through it, by education. So if we look at the E of engineering, by degree that goes into it, you can look at by field. Almost everybody has a bachelor's degree or above, and only a few areas do you see less than bachelor's degree areas. If we go to the S of scientists, you see there a lot of people have PhDs. In some fields, you know, it's over 60% have PhDs to be a scientist. Can you read that? Oh, the top, sorry, my color choice is not good up there, but the top dark bar is PhD, then bachelor's, and then down there the blue is less than a bachelor's. So for the S and the E, you see college is the route into the field, and for S in particular, dominance by PhDs in many areas. Now we get to the T, the mystery category of T, and it looks very, very different. So a little over a third, 40-odd% have a STEM degree. A third have no four-year degree at all. And it's this mix of degrees into the field, very unlike either of the two, which are unlike each other as well. Yet we talk about it as one sort of category. Another way to look at it is by course taking. So this is the number of STEM courses taken by major, and you'll see there you guys are all on the right side here of engineering, heavy STEM course load. On the left are a small number of math majors, and in the middle are your life and physical science and IT down there. So the course content that people are taking looks very, very different. I'll just kind of quickly say we talked about why engineers are very desirable outside of engineering. I think that says a lot. They know how to work hard, take a lot of hard courses. Whatever they may or may not learn, that speaks to it as well. So we get to then kind of the supply point. All right, so you've all heard you know, we're in a race against the world, we're awful, we're going to the bottom, drive to the bottom, et cetera, et cetera. And part of that problem is that, you know, you hear all these tests about all these nations. We hear about Singapore and Finland, right? But when you go to hire, and ask your company people here, you don't hire or move to a company based on its relative size of its workforce. You hire actual workers. So you don't go to Finland if you're looking for high-skilled workers, because there just aren't a lot of people there, no matter what they score. You'd be better off going to a similarly sized Massachusetts, for example, because you also have labor in adjoining states. So we look at the population of where is the world's supply of high-performing students. Where would you go? You see, the U.S., actually, depending on your measure, has the lion's share of high-performing students there. So, okay, but do they make it into STEM? And that's the question, because these are all tests of like middle school students. So if you look at the flow of students from middle school into college and entering the STEM workforce, and somebody can do the math, what % of middle school students do we need to supply the current STEM workforce hiring needs? Anybody's got the math there? Do it quickly. Nobody had any, no takers at the end? 2%. Okay, so maybe my definition's too narrow. Broaden the definition of STEM, double it, triple it, 6%, 8%. Essentially, the STEM workforce is filled from a very, very small segment of, of our student, high school students who are being tested. Now, this is not a defense of bad education, et cetera, but if we're talking about supply into the STEM workforce, it's a very, very small segment, and we have very high-performing students. The problem with the average test scores is it's an average. It washes out, the highs and the lows. And at the high end, we do better than, match or do better than any other place around the world. Put a Massachusetts or Minnesota up against a Singapore and a Finland, and we do quite well. All right, we got that covered. You're all not convinced, because now we have the problem, what about the leap? Okay, so they get into college, and we lose them in college, right? That's true, and we heard about that this morning. 20, 30%, depending on the field, who start out in a major don't end up that way. However, I think somebody yesterday talked about poaching versus flow. It just depends on which side you're looking at. Well, and part of this is a data problem. We have this data set where you can look at a cohort that graduates within 6 years, starting, ending. And one of the interesting things is when you now compare the number who start in the field and graduate, the graduating cohort is slightly larger than the entering cohort. So we lose, but we also have an inflow. So depending on the field, it's a slight increase between freshman year and graduation. And the reason is there are people flowing in to STEM fields after freshman year. And if we look at where people come from, and this was a surprise to me, even in engineering, 25% of engineering graduates didn't start in engineering. Some came from undeclared, but a lot came, 11%, started their college career with a declared non-STEM major and discovered their interest in engineering and flowed in. So it means we also have an inflow into these fields. It's not all a matter of one-way loss out of it. And what happens is, for a lot of 17-year-olds, there's a lot of, people have broad interests, broad skills. It takes a while to develop those. So we wanted to look at what's the potential pool of students who might be recruited or interested in STEM. And so a few measures we had was your science index interest. This is done by the ACT of high school students, so your initial interest. And this is actual numbers. So, a lot go into life sciences, but look at the numbers in humanities, because humanities is very large. So the interest in science really is across the board. If you look at technology, it's also, kind of throughout, that you do have a lot of students who go to college who have interest in science, technology. It doesn't mean they're going to be a scientist or a technologist. But it's there. It's there for performance. It's there from interest. And it could be there. So the last piece of this is, okay, but do we supply enough graduates for the workforce? Are there enough there? And we've seen some of these numbers earlier from same and different data sets that only about 2/3 of graduates in professional fields of health, well, more in health, but engineering and computer science actually go into a job in that field upon graduation. In other words, our universities are putting out a supply 50% greater than the number that are hired each year into those fields. Why don't they go into the fields? And you saw those numbers before. Better job elsewhere, job not available. So you have the desire and you have the supply. They're just not going there. Maybe it's not a supply problem. What's there? And yesterday, I think we heard that from people in industry said, shortage is not an issue. We don't have that. The only shortage problem, I think somebody said, is enough HR people to handle all the applications and sort them. So we don't see it. There are spot shortages, certainly. All right, so in conclusion, kind of the three things. And part of it is, in science, we want to ask the counterfactual about retention, for example. And who here teaches freshman engineering students? Anybody? All right. So let me ask you, would you want 100% of that freshman class to become practicing engineers? Aren't there students there you probably don't want building your bridges, your airplanes? Right? Part of what we do in college is selectivity. Part of the process for the student is search and discovery. That's what college is about. Flow is good. We want people to figure out what they want, what their interests are, come and go, and we want to be selective. It's not like we want all of them out there. So I think the idea about retention and focus on retention is really counter to the way we operate our colleges. We don't set up, say, the German system, age 16, this is what you're going to do, and tough luck if you don't like it. And people talk about that strength of it. We underestimate, as I said, the potential pool and overestimate the leak. Again, I think this is the poaching flow issue. And then finally, I think what this suggests is that attraction should be one of our issues rather than just retention. And to rethink that retention has maybe too much emphasis. It's not the solution. I mean, we don't want to drive the wrong people out, but this single-minded focus on retention is really counter to the way our colleges operate, to the strength of our system, and it's probably productive because it takes away the attention to attraction. And we hear this, well, if you don't start them in kindergarten, you lose them. The data say that's not true, that in fact we can attract people through college, and there's some research suggesting that we should put more emphasis into introductory classes. There's a broad interest of people who can be swayed by what piques their interest, and that happens in introductory classes. And with that, on Kitty's note, I will change. Thank you.
Okay, great. Questions for Hal? I actually have a question for Hal. So the main message is that we shouldn't be panicking, but most things can be improved a little bit. Do you think? Do you have any well, you were actually just starting this at the end, but do you have any recommendations as to how we could improve the matching of students to future occupations?
I think that's a question that some other people talked about who really talk about career choice. I think that's sort of at the micro level of how do people pick careers. And what little I know about it is...
Well, actually, since they did speak about, let's say, not students, but people in general, recognizing that people are changing fields and so forth. So matching workers to the right jobs in general.
Well, I think it's encouraging flow. I mean, that is the strength. And that's one of the things that I think we're getting off the rails with a lot of the retention focus is not recognizing the strength of the U.S. system, which is the flow, the cross-disciplinarity. Steve Jobs and before him, Edwin Land said that, these great companies stood at the intersection, I think it was of humanities and science and technology, that The Silicon Valley experience. I mean, a lot of great innovation, I think particularly more so now, stands because people flow across disciplines, take these things, and so we should facilitate it. If that, I mean, to the extent that we want better match, it's to facilitate flow rather than trying to increase lock-in at an early age. I mean, that's the big piece. And then how to do that, I think, is more of a technical issue that, people who really look at how do you match interests, how are people driven, and, the economists talk about, there's a marginal effect on wages, so that drives some people, and other people it's satisfaction, et cetera. So, did that answer your question? No?
Amy Javernick-Well, University of Colorado. I had a question on your inflow into engineering, and I was curious if those students had not decided yet that they wanted to do engineering, because a lot of the population that inflows into engineering in my school has decided that they wanted to do engineering, but they weren't admitted when they were freshmen into engineering, and they had to do well in a certain number of classes.
Well, what we had on the chart was 11% actually had a declared non-STEM major. So, and then another 15% were undeclared, and presumably some of those were intenders. So some of that inflow is there. But Sherry said that Stanford, 25% don't declare engineering until after they get through. So there are some other studies and people that said that there is a post-freshman flow into engineering where people discover their interests and strengths. And like you, I was surprised because one thinks of that as the hardest place to enter late. And I suspect a lot of that is probably places like biomedical and industrial engineering where it's not there. But there is an inflow. And maybe that's one of the issues about, can you restructure the curriculum in a way that allows that? This also probably includes a lot of 6-year completers, taking extra years to make up the time.
Alan Zimmerman. So this has been across all of the presentations yesterday and today, but it really struck me in your presentation is the recognition of software engineering as an engineering discipline. We are very quick to lump all of computer science as not engineering. And I think there's it came across in your data that a large group are in IT and software. Mm-hmm. And I'm wondering if we're doing ourselves a disservice by counting all computer scientists as scientists and not recognizing that just like there's different other engineering disciplines, some are engineers, some aren't. There's a subset of the IT and computer science who are in fact software engineers, either by training or by practice.
Well, I think we usually do count CS as an engineering field, so in the numbers. But your presentation,
you counted it as S. IT and computer science, you said is S, not E. And
no, I broke it out separately for that very. I agree with you, and I broke it out separately for that very reason, as I put them in the IT category. It's the answer is yes, you're right. That most of these my takeaway point on that is most of these classifications are very ill-defined, and one has to start, in fact, with what's the purpose? There is no good classification. If you go through it, nobody has the definitive classification, and it needs to be driven by the question. What is your question? Is it education? Is it occupation? Is it contribution to innovation? And then you work backwards to decide who you want to include and how you want to count them.
Well, it's just, and the reason I'm asking it is it's such a large number. It's a large percentage in your presentations and in the presentations earlier, and a lot of the presentations yesterday acknowledged, biomedical is a large percent of other. Well, if it's such a large percentage of other, then it probably deserves to be broken out in some of these
I think we have a couple more questions. I think we need to whip onto them before we go to...
Professor Salzman, thank you for breaking out the T. But in your presentation, you showed us the T, the inflow in T. By the way, I'm Michael Darnforth from Purdue University. You showed us the inflow from T for the IT professions. Does your analysis also include the other components of T?
What would they be?
Well, there's an awful lot of engineering technology out there: mechanical engineering, electrical
Oh, that's-
engineering, aviation.
No, that's
technology.
that's the E. I thought you meant the T is usually exclusive of engineering.
Well,
I-
with all due respect, there is a profession of T, and
Right.
I was curious whether your analysis included that. I'd be pleased
Well-
to show you the data on those.
Right. No, I agree with you, and I think that's part of my point. Is it's a very muddied category that you have engineering at the 4-year level. You have engineering fields, and the T, the non-engineering T, at a 4-year level is very, very small. It's a couple percentage points. Most of the T is 2-year degrees outside of engineering. Okay, well, I would be interested in the data, because if they're there, they're not being captured well. So that is an important point.
Okay, hi, Ann Reimers. I'm an Einstein Fellow with Department of Energy. So as a high school teacher, I want to say that some of the reason I think that people get to college and then decide they want to be engineers is very, very few high schools have any kind of even exposure to what engineering is. And so these people don't even know what engineering is until they're at least a semester in. So colleges might try to make it a little bit easier for them to move into the field. It is extremely difficult to move in later if you don't start right away. But my question is that high schools do have career and technical education. So part of that T are people that come right out of a technical sort of training program in high school, don't go to a 2-year college. Do we have enough people doing that or coming from 2-year degrees to fill the lab technicians and other sort of technical, lower than college level, lower than 4-year college level people? Do we have enough of them?
I haven't looked at that as much, but I don't see any data suggesting that's the case. The shortage issue is a longer discussion and depends on which piece you want to talk about it and all the particulars. And there are some areas. In fact, I show you if you want to. Petroleum engineering was an area where there was a shortage for a lot of reasons. And what happened is salaries went up and graduates tripled. So the other point is the market seems to respond. And we do not find many, if any, cases where the market sends a strong signal that it's looking for students, and albeit with a lag because it takes a while to prepare them, there isn't a very strong response. And generally, the problem is that not using the market. I'm not a big market fan. I'm a sociologist, but that said, there are very few cases where in the labor markets you see a strong labor market signal that you're looking for people and you don't find the response, even at very technical fields such as petroleum engineering. And we've looked and looked, and it seems to be there. And when we find hiring shortages or difficulty in hiring, other than a short-term lag, it's either unrealistic expectations or not paying what it may take in the market to gain those people.
Okay, great. So let's go on to Larry's presentation. Thanks.
I'm going to talk about 3 things. I'm going to talk about the implications of this picture for undergraduate education, focusing on objective 3 of our project overview. Then I'm going to give my elevator pitch for a new program I'm proposing that will solve all of our problems. And then third, I'm going to raise some questions for the committee to pursue. What is this? What do you see in this picture? Well, we've seen enough like it. I'm not going to quibble or argue about the data. It's from a paper by Burton and Parker in 1998, so in a way it's dated. But it is, there are 2 million people here that were sampled, 2.2 million people. It's from an issue brief of the Division of Natural Science, the Division of Science Resource Studies of the NSF. And as I say, it was published in 1998. And it shows that of the 2.2 million persons surveyed claiming to have a degree in engineering, that's the big circle sticking out on the left, 1 million of them stated that their principal occupation was not in engineering. They reported that they were not doing engineering. And in addition to the other 1.2 million working as engineers, another 0.4 million claiming their principal occupation was in engineering did not hold an engineering degree. Again, we've heard this yesterday and today. What does it say? It says that many of our graduates, around 40% and up, sooner or later are not doing engineering, supposedly. Now, what might one infer from this data? Some of us might look kindly on this data, seeing this movement of degreed engineers into other fields as leakage in the engineering pipeline. And I'm quoting the project overview. And therefore, a net loss of potential and real engineering talent to less productive activities. On the other hand, we might claim that here is evidence that engineering education provides a foundation for a wide variety of good careers other than engineering per se, engineering narrowly defined, and view this movement of degreed engineers into other fields in a positive light as an unrecognized net gain for the nation, the economy, and employers. Or we might step back, and I conjecture that those that say they are no longer doing engineering are actually doing what you or I would say is engineering, but it's not what they were led to believe engineering work to be by their teachers, by the courses they were required to take, the problems, the single answer problems they were required to solve each week. So if we see this movement as leakage, then one reaction might be to strengthen our efforts to attract more youth into engineering to make up for the lost. We do a lot of things we are trying to do, and whatever. But the implications for what we teach in our hardcore curriculum, how we teach, or who we omit, implications are nil. There's nothing wrong with what we're teaching. That's engineering as it is. The questions about implications for our programs, other than add on a few things, never arise. If, on the other hand, if we think it's a good thing that engineering education is foundational in its broad sense, the first observation, and find that my conjecture may have some truth to it, that students, let's say, are being misled or not being shown the light or the complexity of engineering, then it strikes me we have to think hard not only about what we are telling our students explicitly about what engineering graduates do, but we also have to think hard about the values we convey in setting our requirements, in the ways we teach, and in our mission requirements. So how we respond depends upon how we see our students and their futures. And this, of course, informs what we see as our purpose in teaching. If our focus is on the industry needs, and we see our students as products for industry, for example, I've heard that phrase, at least in the past, or a commodity, then most likely we see this movement as leakage, and the implications for our teaching are nil. If, on the other hand, we focus on the student, the individual, their growth, self-fulfillment, whatever, so-called soft words, and advise career counseling, then we might, and furthermore, you can turn this, how do I turn this off? Thanks. I want to turn the slide off. I want to move to, if we look at what's going on in industry, for example, in professional practice, and we see that doing engineering requires more than solving well-posed problems in one's own specialty, alone with what I have labeled an object world, then that connecting with stakeholders and coworkers who may live halfway around the world, who have a legitimate say in product development effort or a public works project, requires the ability to comfortably handle different perspectives. And it demands acceptance of the fact that in many cases, an engineering task will not have a well-defined, quantitative, nonetheless optimal solution, and that ambiguity and uncertainty pervade the problem space, the challenges that challenges the authority of instrumental rationality. Then a more qualitative form of reasoning is required. The professional has to be contend with multiple framings of events, to critically reflect upon their implications, and be willing to negotiate with others who see the world in other ways than we. So what the implications are of these observations for undergraduate education? If one were to ask me how well aligned are the skills and knowledge acquired in formal engineering education with the skills and knowledge needed on the job, I would say they're not very well aligned. And I think that message has been said probably not as hard as I'm saying it. So I now move to my elevator pitch. These thoughts, these observations over 40 years of teaching engineering, and trying to do something about it to broaden engineering education, have led me to propose, with some colleagues, several of whom are in this room, a new pathway, a new undergraduate degree program, a new pathway to the profession. The program is meant to be a Bachelor of Arts in, let's call it, liberal studies in engineering, and it's meant to attract students undecided about choice of a major, but who have sufficient interest to enroll in a program that keeps open the possibility that they might pursue a career in engineering. For these individuals, the program will offer a smoother pathway into the profession, as you know, a year or two additional. For others, it will serve as a new liberal arts program centered on STEM. Now, here's the core idea. It would take exemplary, substantive content of the traditional engineering coursework, the engineering sciences, laboratory tests, design projects, but subject it to study from the perspective of the humanities, arts, and social sciences. In a way, I'm saying, put the humanities, arts, and social sciences in charge. You have engineering content, but the engineer is now the soft skill, let's say. Or let's not say the soft skill, but, well, let's get to that. The program would build upon existing degree programs oriented towards engineering that already exist. For example, an unaccredited AB in engineering at places like Harvard, Lafayette, whose flexibility with respect to requirements might allow the infusion of a set of core courses throughout the undergraduate years. I would also argue that this program should develop a sense of community in the students, so there has to be some persistence of the courses throughout it can't be just designed the first year and capstone the last year. It has to persist. It has to define the student's intellectual identity in a sequence of core courses. Now, what else? Well, what else? That depends upon the institution. Could be they minor in engineering. Could be they minor in literature. Could be they're pre-law, pre-med. Liberal arts colleges offering 3-2 programs in concert with an engineering school, and even community colleges that have historically seen a significant number of their students go on into engineering at university will also be approached. Why not? The plan is to research and explore possibilities at these different possible venues. This is not a new idea. Think of this as a first professional, because the first people have proposed the first professional degree be the Masters of Science. For example, we read in NAE's publication, Educating the Engineer of 2020, the baccalaureate degree should be reorganized as the pre-engineering degree or Bachelor of Arts in Engineering degree, depending on the course content reflecting the career aspirations of the student. Well, that can be interpreted, I think, to allow this as a possible option. And other authorities like Jim Duderstadt, who is on our advisory panel, claim that adequate depth in a specialized area of engineering cannot be achieved in the baccalaureate degree. And I've recommended the same, that the first degree should be like in law and medicine, a liberal arts degree. Where is this going to take us is unknown. We have a workshop scheduled for the end of January, right here, hosted by NAE and funded by NSF. And we signed up a list of resource people from the humanities and social sciences, as well as engineering, about half and half, who have expressed interest in helping to the extent of their interest and of time available. Some of them have contributed significant time. The problem, like any authentic engineering design problem, is inherently social. Note that the range of, I'll now turn to generate some questions for you. Note that the range of possible venues for a program in liberal studies in engineering is broad. We are approaching liberal arts colleges offering 3-2 programs in concert with an engineering school. I'm talking with people at Emory down in Decatur this next week. I would extend the scope of Objective 2 as it's presently stated, seeking to get a grip on the factors that influence the career decisions of those working as engineers, to include the career decisions made of students who aspire to work as engineers. And this would include students who sign up to do a 3-2 program at a liberal arts college. And also, I'd look at, maybe you're already doing this. Of more general interest, at least to our project, is what is the state of these 3-2 programs? How many students do they attract? How many complete the full 3-2 course of study? How many drop out along the way, and why? How do engineering graduates of these programs do in practice? What fraction of them stray? Are they happy? Or is it a scam to attract students to your liberal arts college? Returning to the question of alignment of our curriculum, our ways of teaching, our admission criteria. There's one dimension we've talked about of the undergraduate experience that needs attention. I'm thinking of the co-curricular activities and how they have come to play a bigger role in the learning experiences of undergraduates. I think we would agree that that is the case. I'm not sure these activities have been successfully taken into account and recently end. Okay, all right. So I think these co-curricular activities should be paid more attention. Finally, I think there's a bigger question here, a more fundamental question, and it won't be solved by preparing our engineering faculty to be better teachers. We have to ask the question, what do engineers really need to know to function as engineers across a wide variety of possibilities? What is fundamental? What should we be teaching? Not so long ago, we might have had a ready answer at hand. The fundamentals we should teach are the fundamentals of engineering science. That's it. This response is wholly consistent with a way of seeing rooted in the belief that engineering knowledge, thought, and practice, like scientific theory, stands free of cultural context, national or individual identity, value, and needs. Hence, all students, regardless of race, socioeconomic status, cultural origins, if they're smart enough in math, should be able to learn engineering. Like Newton's laws, engineering knowledge rests independent of social context, cultural context. If, on the other hand, our way of seeing is rooted in the belief that engineering knowledge, thought, and practice depends very much upon context, historical, industrial, natural, cultural, and that also students are good in math, and that students of diverse origins and status bring different experiences and potentials to the table, but still are good in math, then engineering knowledge needs to be broadened to engage this diversity. Engineering work still requires Newton's laws, but it requires much more. It's not just soft skills.
Okay, you need to wrap up.
Thank you.
So I was going to give times for questions just for Larry, but I think he took up his allocated question time. So general questions to any of the panelists. We have a candidate there.
Emily Allen, Cal State LA. My question's for Larry, but also more widely. There's one occupation that some engineers enter that hasn't been mentioned in these 2 days, and that's teacher, K-12 teachers, particularly middle school and high school. And Larry, I wonder if you've thought about your degree as a precursor to teaching credential, STEM teaching credential.
Yes, it's quite open. What students, let's say, concentrate in, let's use that word instead of major. Let's say they major in liberal studies and in engineering, would be dependent upon what they do outside of this core now, and dependent upon the institution and the resources available and faculty interest. So teaching could be very much a part of that. Why not? I mean, students from MIT go on to teach K-12, and this would be another route. But the idea would be that open to all possibilities, to those variety of careers. So pre-professional, where professional can be many different professions.
I actually have a follow-up question myself for Larry, since no one's jumping up. I remember hearing MIT make exactly this proposal 20 years ago, and in fact there is a 5-year electrical engineering, in any case, degree at MIT, if I'm not mistaken, but almost nobody actually does it, so it doesn't seem to have taken off.
I think there was a general engineering degree many, many years ago. Let's think of programs that exist these days that are intended to be of this sort. Like there's a liberal arts and engineering program at WPI, which has 2 students in it. And the reason is, I think, is because they're defined in terms, engineering or these programs are defined as what I call patchwork programs, so that as the requirements are stated as you must take this many engineering courses, but they're just a reduced number of the courses that the full major would take, and you must take this many courses in the humanities. And of course, there's an advisor that has to approve it. Well, those, nowadays, that's becoming more and more popular, this kind of smorgasbord approach, this kind of disintegration of the curriculum into half courses and online. I'm all for online where it works, but I think we should think hard about what the undergraduate experience is for. It's not just for preparing students with certain skills. It's really trying to prepare citizens, reflective practitioners, in the words of Donald Schoen. We have a responsibility here. I'm sorry. to lecture like this, but I think we have a responsibility that goes upon filling our students up with certain skills.
Al Bunshaft, Dassault Systems. I have a quick comment and a question. I want to appeal to this whole group, and I said it to some of folks at the break, and it seemed to resonate. We as a community need to stop using the term soft skills. And Amy made the point, she called it professional skills. In the Innovation Task Force I'm part of, we call it employability skills. These are essential skills that I believe, and the industry reps in our committee believe, are not being sufficiently taught by educators and make the difference between young employees being productive or not when they arrive at work. My question is about the attraction topic. I agree that attraction is a more important issue for us than retention. I have a very small sample size. I'm not a university professional, but from my sample size, it's very difficult for non-majors to get access to introductory courses because the students who are majors get first priority, and often it's forced until like junior year before they can take introduction to computer science or engineering. Is that a constraint in our educational system broadly, that there are actually more students that want to take these introductory classes than can get access to them? And what are we doing about it, or what should we be doing about it? I think it is.
Not in sociology. We'll welcome lots of introductory students or planning and policy. I think it is a constraint. I think as important, and I think there's some research there, is that we don't pay enough attention to them. That we think of them as kind of, the throwaway large 200-300 student course, rather than understanding this is the time when students are developing their interests, and if we want to attract people, we ought to be putting attention into who's teaching them and what we do in them, as the entry portal. And I think we should think about them differently from a lot of different angles.
So I want to respond to that very quickly. Kitty Diddy and NAE. There are definitely capacity issues in public universities. And particularly if you look at 2-year to 4-year transfer students, NAE has had a project looking at 2-year, 4-year engineering technology students. And I know Emily and probably some of her colleagues from the Cal State system and others can talk about capacity issues where you actually have exactly that problem, where you have students who need to have a certain amount of credits in order to transfer, and they can't because they can't get access to these classes. So there's a huge differential between an MIT or a Bucknell than if you're a 2-year state system or a 4-year state system. And what you have also, which hasn't really been raised, is differential tuition now being charged in many cases for engineering students. That's having an impact. So someplace like UTEP in El Paso, what they were finding is their full course load is, I think, 16 credits. And what they were having is they were having students coming in and taking the 16 credits, and they would drop a class, very common practice, and these students would no longer have their federal funding or any of their financial aid because you have to be a full-time student. So they've actually changed now where they tell their students, you take more classes than you need, but then that has a disparate impact on who can actually be enrolling for the classes. So the capacity is an issue for state campuses.
I think back of your slide where you showed the number of credit hours that engineers take compared to other disciplines, and that was really quite striking. And that, I think, certainly places a limit on when students might move in. But I think that lockstep kind of curriculum, and you hear in engineering faculty meetings about why we can't do more about these professional skills. Why can't we have students involved in studying context, doing more design? And the answer usually comes out, we don't have room in the curriculum. There's not enough time. Well, if you think of knowledge as stuff and that it's embodied, it's countable, then you end up nowhere in those discussions. You end up not changing anything. And I think that's been the course of the past 20, 30 years. So if, however, you say, let's move away from that idea, and I think people are moving away from that idea that a course in mechanical engineering require all of these credits, to prepare the student to graduate for a variety of careers within mechanical engineering, and you move to something like the course 2A, which is at MIT a more flexible curriculum, which encourages interdisciplinary kind of study in biomechanics and things like that. Originally, it was a program for dropouts, but now it's accredited, and so it attracts more students than the core curriculum. There is this move, I think, towards more flexibility in the curriculum. If you accept that that's a possibility, then it opens up the door, at least a crack, to the possibility that you can move away from this idea that the student in mechanical engineering or whatever engineering must have all of this stuff to graduate.
Hi, I'm Dave Nagel. I'm a member of the committee. Larry, I want to ask you to explain something because I may have misunderstood what the point you're trying to make. How I heard it was that you were expressing concern that students could actually get, by the time they've completed a bachelor's, all of the technical things that they really needed to have to be productive as an engineer. That may not have been what you said, but that's what I heard. And then I heard you then advocating that extra finishing, or whatever you want to call it, would happen at the master's level.
I think there's I make a difference between what a student is capable of after doing something, studies, internship, Engineers Without Border, which is an individual decision, and the notion of certification or accredited degree. Now, let's say we had set up this liberal studies in engineering program, and the student effectively minored in an engineering discipline. All right. I'm not going to say to that student, you can't interview a company and go to work for them. Maybe one that he's interned with or she's interned with, but they won't have the accredited degree necessarily, okay? But I would hope that the student might go on for a master's maybe in just one additional year depending on what they did with their, let's say, free electives. But the point is that the core would be move away from the rigidity of what we have now.
I'm going to ask a question that might again be for Larry, but for any of the panelists or indeed people in the audience. So one of the issues we're discussing is how well universities prepare their students for employers. But I want to make a distinction between how well they prepare the students for day one on the job and maybe for year 10 in the job, which could be completely different things. And in particular, in my area, the distinction of importance here is business undergraduates and economics undergraduates. I have no doubt that on day one, the business graduate is a lot more useful. I'm sure the economics one's pretty useless on day one. But in year 10, I put my money with the economics graduate, and in fact, it does seem to be the case that economics earnings rise faster with age than business graduate earnings. And so similarly with engineering and with Larry's proposal, so Larry's proposal, I bet, makes the people worse on day one. But in year 10, it could be a completely different story. So I was wondering if you or anyone else wanted to elaborate on that.
Yeah, I think the emphasis would be on lifelong learning. And that means broader than what it may mean to engineers as continuing to keep pace with advances in your discipline. I mean, lifelong learning and the ability to investigate other fields that might interest you, or how does what I know apply and what I've learned to this other possible enterprise, or maybe in starting up a company. So yes, I would agree that the focus is on the student and their future career, lifelong learning, not on the first day of the job. Because, well, we've seen from the data that can you really do that?
Can I add something first?
Oh, sorry.
We talked about internships earlier and how they're useful for retaining students within engineering. One of the things that our data are showing are that internships in particular enable students to learn on the job more effectively than other co-curricular experiences. So if a student arrives with some skills gap, they're able to hit the ground running more quickly than a student who doesn't have that experience on the job. So it takes them a little bit longer to develop those skills once they're in the workforce. So I think thinking about identifying those experiences in higher ed that enable them to be more, better lifelong learners can develop these on-the-job skills more quickly is something important to look at.
Hi, Ann Reimers again. So we're saying, maybe it's just the name liberal arts and engineering. What if it were called something like cross-curricular engineering? Because all the industry people that are getting up here are telling us that they want for their engineers to be able to understand and work with people in other disciplines. So this should be an attractive major for them. If they really want an engineer that has experience, or at least some experience and some vocabulary and ability to work with people in the different disciplines of engineering, but then maybe 2 solid years or 2.5 solid years of a particular discipline, then there's no reason why they shouldn't consider them a full mechanical engineer, but one that has a broader reach and ability. 5 years is probably the minimum of what you'd be able to do in this, but I like the idea. And it should be attractive. The other thing I'd like to say is that saying that there's not enough time in the curriculum to put in the sorts of skills that you need is exactly what's going on right now in K through 12 with the idea of next generation science standards and Common Core. So what the teachers are learning is that you just have to change the way that you teach. You can teach the exact same content material, but through project-based learning, cooperative, writing, presenting. The students are doing more work, you're doing less work. You're not lecturing anymore. They are teaching each other. You get the exact same amount of content material done. You should be able to do it in engineering as well, but you also have the students experience those employability skills. Thank you.
I think in a way, K through 12 teachers are ahead of us in engineering faculty, in adapting and innovating in terms of the things you said. In terms of the name of liberal studies engineering, that's, it could be social engineering, humanitarian engineering, Colorado School of Mines. The point is, my reason going is as follows. The important thing is to broaden the context, as the late President Vest argued, to broaden the context of the problems that students are challenged with. We don't just give them single answer, well-posed problems that have a unique solution, because they don't exist. I mean, usually, nonetheless optimal. But the problem usually is, what is the problem? Or why am I solving this problem? Or further yet, who benefits by me doing this problem? I have this problem with this ignition switch that seems to be faulty. Do I take the initiative? What should that initiative be? Who do I talk to? I should be talking to someone. Who are my collaborators? Well, if I don't have any, I'm in trouble. I've got to have some resources there. Otherwise, I'm going to end up with the short end of the stick, as he has ended. So, these are important issues, and they're about broadening the context of the problems we challenge our students with. And that once we do that, we confront the social, the political, as well as the financial. We're in deep trouble. There is a new kinds of fundamentals that aren't answered by symbolic expression, deductive relationship, or inferential reasoning, but they're answered by qualitative argument, negotiation, and the sciences of the social sciences and theories that developed even in literary criticism. So I think broadening, once you open that up, then there's really quite a lot to do.
I was talking yesterday about the opportunity for industry to offer professional development for faculty members, and one of your Einstein Fellow colleagues suggested that collaborations between K-12 teachers and engineering faculty members could serve the same purpose. We often think about engineering faculty delivering content to the K-12, and here's what we do in engineering, but I think it could be a two-way street back and forth, bringing in some of these new pedagogical techniques into the higher ed sector. So I think you're spot on that K-12 teachers are certainly more forward-thinking in terms of their teaching. Yeah.
This is sort of Lynn Epps, University of Delaware. Wanted to sort of touch on what you said about bringing employers in. I think there's a huge opportunity we leverage employers to do resume workshops and interview skills. It sounds like there's another huge opportunity to bring those employers in to help facilitate the professional skills types of workshops. Employers or employees aren't necessarily getting academic credit once they're in the workforce for going to those types of workshops. And so there's an opportunity, I think, a huge opportunity, because employers want to get in front of students. And so this is another unique way to bring the employers in, maybe via career services or faculty, however you determine to facilitate those connections. But I think it's a huge opportunity so that the faculty aren't necessarily feeling as though they have to facilitate that that training. And employers are getting access to top talent by helping, facilitate those types of that development.
I think I agree. I would probably add to that and invite faculty members to those sessions too, because if we just focus on students, then we have to do that professional development for every cohort year after year. And faculty members might pick up some ideas on how to tweak what they're already doing in their classes based on those workshops also.
Okay, so that's we're going to end here. Kitty may have some instructions for us. Do you, Kitty?
Thank the panel.
Well, okay.